there is something strange happening around Saturn. For most of human history, Saturn has looked the same. A pale yellow world, wrapped in enormous rings that seem timeless. When Galileo first pointed a telescope toward it in 1610, he didn't even understand what he was seeing. That Saturn's rings were ancient, that they formed when the planet itself was born, but that assumption was never tested. Which leads to a much bigger question. If Saturn didn't form with its rings, then where did they come from? And what kind of event could create something this vast around one of the oldest planets in the solar system? This is the story of how Saturn got its rings. Millions of years ago, Saturn had an extra moon, perhaps 400 kilometers across, formed almost entirely of ice. But this moon was doomed. It was orbiting just too close to resist the immense forces of Saturn's gravity. There's an invisible boundary around every planet called the Roche limit. It's the distance at which a planet's gravity becomes strong enough to tear apart any object that ventures inside. The exact location of this limit depends on what the object is made of. For an icy moon, the Roche limit is farther out than it would be for a rocky moon. The theory suggests that this ice moon approached Saturn's Roche limit. Maybe it was pulled inward by gravitational interactions with other moons. Maybe it was struck by a comet, nudging it into a decaying orbit. Either way, once it crossed the Roche limit, the outcome was inevitable. Saturn's gravity pulled harder on the side of the moon closest to the planet than on the side farther away. The difference in gravitational force, the tidal force, was strong enough to overcome the moon's own gravity. The moon began to rupture. It didn't happen slowly. The moon was ripped apart catastrophically. Up to 17,000 trillion tons of ice broke apart in orbit around Saturn, and thanks to the speeds this material was traveling, it likely spread out to encircle the planet within just a few days. Saturn's iconic ring system was now in place. This theory is elegant. It explains the rings' composition almost entirely water ice. It explains their location, right at the Roche limit. But it has problems. If a moon was destroyed by tidal forces, we'd expect the debris to spread out gradually. It would take time for the material to settle into the flat, organized rings we see today. Computer simulations show that this process would take tens to hundreds of millions of years. That's consistent with the ring's estimated age. But there's a catch. The debris from a destroyed moon wouldn't naturally form into the precise structures we observe. Saturn's rings aren't just a uniform disk of particles. They're incredibly organized. They have gaps. They have ringlets. They have shepherd moons that keep certain rings confined. The Cassini division, the largest gap in the rings, is 4,700 kilometers wide. It's not empty, but it's much less dense than the regions on either side. The Encke gap, within the A-ring, is maintained by a tiny moon called Pan, which sweeps up particles as it orbits. These structures require more than just a moon breaking apart. They require specific gravitational interactions. And here's the bigger problem. Saturn's rings are aligned almost perfectly with the planet's equator. But Saturn's equator is tilted 26.7 degrees relative to its orbital plane. That's a substantial tilt, larger than Earth's. If a moon was simply torn apart by tidal forces, why would the resulting debris settle into a plane aligned with Saturn's rotation rather than its orbit? The simple ice moon theory doesn't explain that. And it doesn't explain another peculiarity. Saturn has over 140 moons. Most of them orbit in roughly the same plane as the rings. Their orbits are circular. Their inclinations are low, but one moon is different. Iapetus is Saturn's second largest moon after Titan. It orbits at a distance of 3.5 million kilometers from Saturn, far beyond the other major moons. And it's bizarre. First, Iapetus has a two-toned surface. The leading hemisphere, the side that faces forward as it orbits Saturn, is remarkably dark. It's coated in material that's as black as asphalt. The trailing hemisphere, by contrast, is bright and icy. We now know that the dark material comes from Saturn's outermost ring, the Phoebe ring, a vast, diffuse structure that extends millions of kilometers from the planet. Particles from this ring slowly spiral inward and coat Iapetus's leading hemisphere. But that's not the strange part. The strange part is Iapetus's orbit. While all of Saturn's other major moons orbit within 1.6 degrees of the planet's equatorial plane, Iapetus is inclined at 15.5 degrees. It's wildly out of alignment. And there's more. Iapetus has an equatorial ridge. It spans 1,300 kilometers across the moon's surface, nearly its entire diameter. The ridge is 20 kilometers wide and rises to a height of 13 kilometers. It follows the equator almost perfectly. No other moon in the solar system has a feature like this. Why is Iapetus tilted? Why does it have this ridge? And why do the other major moons Titan, Hyperion, Rhea, Dione, Tethys, Enceladus, Mimas all have slightly eccentric orbits when they should be circular? The ice moon theory doesn't explain any of this. So, scientists began looking for a different explanation, one that could account not just for the rings, but for these strange orbital properties, for Saturn's axial tilt, for the gaps in the ring system. And in 2022, a team led by MIT's Jack Wisdom published a new theory. It's radical. The theory starts with a moon that no longer exists. The team called it Chrysalis. It was comparable in mass to Iapetus, but it orbited much closer to Saturn, somewhere between Titan and Iapetus. Its orbital period was about 45 days. Chrysalis wasn't alone. Titan, Saturn's largest moon, was also there, and the two bodies were locked in a gravitational dance. As Chrysalis pulled on Titan, it gradually pushed Titan outward. Titan's orbit expanded, its eccentricity increased, and as Titan moved, it began to influence the orbits of other moons, Hyperion, Iapetus. At the same time, Chrysalis itself was being pulled inward. Tidal interactions with Saturn and gravitational tugs from Titan slowly dragged it toward the planet. But there's another factor at play here. Saturn's axis doesn't just tilt, it also precesses. It wobbles, like a spinning top, completing one full cycle every 83 million years. And here's where things get interesting. Saturn's precession period is almost identical to the precession period of Neptune's orbit, 1.87 million years. This isn't a coincidence. It suggests that Saturn and Neptune were once locked in a spin-orbit resonance. Saturn's axial tilt was influenced by Neptune's gravitational pull, but for this resonance to exist, Saturn's rotational properties had to be just right. And one of the factors that determines those properties is the distribution of mass around the planet, specifically the mass of its moons. Titan plays a huge role in this. It's Saturn's largest moon by far, and its position relative to Saturn affects the planet's spin. But Titan wasn't always where it is today. It was closer. And when it was closer, Saturn's spin responded differently to Neptune's influence. Chrysalis, orbiting between Titan and Iapetus, was part of this system. Its gravitational effects contributed to Saturn's rotational dynamics. It helped maintain the spin-orbit resonance with Neptune, but Chrysalis was unstable. Over time, perturbations from other moons nudged it closer and closer to Saturn. Eventually, it crossed a critical threshold. It entered the Roche limit, and Saturn tore it apart. When Chrysalis crossed the Roche limit, it didn't have a chance. Saturn's tidal forces overwhelmed the moon's gravity. The side facing Saturn was pulled harder than the side facing away. The differential force was immense. Chrysalis shattered. But this wasn't just a simple breakup. Chrysalis was differentiated. It had a rocky core surrounded by an icy mantle. When it entered the Roche limit, the icy outer layers were ripped away first because they were less dense. The rocky core stayed intact for longer. Eventually, even the core broke apart. But by then, the icy debris had already spread out along Chrysalis's orbit. This debris didn't fall straight onto Saturn. It stayed in orbit, and over time, it settled into a flat disk. The disk aligned with Saturn's equator because that's where the gravitational forces are balanced. That disk became Saturn's rings. The destruction of Chrysalis also had another effect. It changed Saturn's rotational properties. With Chrysalis gone, Saturn's spin axis shifted slightly. The spin-orbit resonance with Neptune broke. Saturn's axial tilt stabilized at its current value of 26.7 degrees, and that tilt explains why the rings are oriented the way they are. The Chrysalis hypothesis is compelling, but it's not proven. It's a theory, a model, a simulation, so what evidence supports it? First, the age of the rings. The Chrysalis model predicts that the rings formed between 50 and 150 million years ago. That's consistent with Cassini's measurements of ring rain and mass loss. Second, the composition. Chrysalis was an icy moon. When it broke apart, it would have scattered mostly water ice, exactly what we see in Saturn's rings. Third, the alignment. The rings lie in Saturn's equatorial plane because that's where the debris from Chrysalis naturally settled. Fourth, the axial tilt. Saturn's 26.7-degree tilt can be explained by the loss of Chrysalis and the breaking of the spin-orbit resonance with Neptune. Fifth, the orbital properties of the moons. The eccentricities of Titan, Hyperion, and Iapetus can all be explained by the gravitational interactions that occurred when Chrysalis was still present. Sixth, Iapetus's inclination. As Chrysalis pulled Titan outward, it also perturbed Iapetus's orbit, increasing its inclination to 15.5 degrees. And seventh, the gaps in the rings. Many of the gaps are maintained by gravitational resonances with Saturn's moons. But here's the thing. None of this proves Chrysalis existed. We have no direct evidence of this moon. It's gone. If it ever existed, it was destroyed millions of years ago, and all that's left are the rings. So, the Chrysalis hypothesis remains just that, a hypothesis. But it's a good one. The Chrysalis hypothesis isn't the only explanation for Saturn's rings. There are other theories, other models, other possibilities. One alternative is the comet-moon collision theory. In this scenario, an icy moon was orbiting Saturn in the inner region of the planet's system. Then, millions of years ago, a comet or a centaur, a small icy body from the outer solar system, slammed into it. The collision shattered the moon. The debris spread out, and over time, it formed the ring system we see today. This theory has some advantages. Comets and centaurs are known to have eccentric orbits. They can approach Saturn at high velocities. A high-speed impact would generate a lot of small debris, which is what we see in the rings. The comet-moon collision theory can also explain the rings' youth. If the collision happened 100 million years ago, the rings would still be relatively clean and bright, just as Cassini observed. But this theory has problems too. First, why would the debris settle into Saturn's equatorial plane? A comet approaching from outside the Saturnian system wouldn't naturally orbit in that plane. Second, what happened to the impactor? If a comet hit a moon, we'd expect to see some rocky material mixed into the rings, but the rings are more than 99% water ice. Third, why is Saturn's axial tilt so large? A collision wouldn't explain that. And fourth, why do Saturn's moons have the orbital properties they do? A single collision wouldn't perturb the orbits of multiple moons in a coordinated way. So the comet-moon collision theory can explain the rings, but it struggles to explain everything else. Another theory is the trans-Neptunian object, or TNO, disruption model. In this scenario, a large icy body from the Kuiper belt, the region beyond Neptune, passed close to Saturn during a chaotic period in the early solar system, perhaps 4 billion years ago. As the TNO approached Saturn, it crossed the Roche limit. Saturn's gravity tore it apart. The debris formed the rings. This theory ties into the NICE model, which describes how the giant planets migrated to their current positions early in the solar system's history. During this migration, the Kuiper belt was destabilized, and many TNOs were scattered inward. But there's a problem. The nice model suggests this happened about 4 billion years ago. But Saturn's rings are only 100 million years old. That's a discrepancy of nearly 40 times. Some researchers have tried to reconcile this by suggesting that the rings formed more recently, long after the nice model migration. But that requires a TNO to be on a Saturn-crossing orbit much later in the solar system's history. And that's unlikely. So the TNO disruption model struggles with timing. Each of these theories has strengths. Each has weaknesses. But the chrysalis hypothesis stands out because it explains not just the rings, but the broader Saturnian system. Still, it's not settled science. Not yet. If chrysalis existed, its destruction didn't just create the rings. It likely created some of Saturn's inner moons as well. Enceladus, for example. Enceladus is a small moon only 252 kilometers in radius. It orbits at a distance of 238,000 kilometers from Saturn, just beyond the main ring system, and it's one of the most geologically active bodies in the solar system. Cassini discovered that Enceladus has geysers at its south pole. These geysers shoot plumes of water vapor, ice particles, and organic molecules into space. The material doesn't all fall back onto Enceladus. Some of it escapes and forms Saturn's E ring, a vast, diffuse ring of icy particles that extends for hundreds of thousands of kilometers. The geysers suggest that Enceladus has a subsurface ocean, liquid water beneath a thick shell of ice. And that ocean is being heated by tidal forces. But here's the puzzle. Enceladus is small. It shouldn't have enough internal heat to maintain liquid water. And yet, it does. Some scientists believe Enceladus is young, that it formed relatively recently, perhaps 100 million to 1 billion years ago, from the debris of a destroyed moon. If that's true, Enceladus could be a remnant of chrysalis. The same might be true for some of the other inner moons: Atlas, Prometheus, Pandora, Janus, Epimetheus. All of these moons orbit near or within the ring system. All of them have low densities, suggesting they're made mostly of ice. They might have formed from the same debris that created the rings. Saturn's F-ring is one of the strangest features in the ring system. It's narrow, only about 500 kilometers wide. It's dynamic. Its structure changes over timescales of hours, and it's shepherded. The term shepherd moon refers to a small moon that uses its gravity to confine ring particles into a narrow band. The F-ring has two shepherd moons, Prometheus on the inside and Pandora on the outside. At least, that's what scientists thought for decades, but it turns out that's not quite right. Recent observations from Cassini revealed that Pandora isn't actually shepherding the ring, only Prometheus is. Prometheus orbits just inside the F-ring, and every time it passes by, it pulls on the ring particles. It creates waves. It draws out streamers of material. Pandora, on the other hand, doesn't have the same effect. It's too far away. So the F-ring is confined not by two shepherd moons, but by a combination of Prometheus and precession, the slow rotation of the ring particles' orbits. This is a subtle distinction, but it matters. It tells us that the dynamics of Saturn's ring system are more complicated than we thought. And it raises questions. How did Prometheus end up in the perfect position to shepherd the F-ring? Was it formed there, or did it migrate inward over time? If it migrated, that suggests the ring system itself is evolving, that the moons and rings are still adjusting to the aftermath of Chrysalis's destruction. Saturn's rings are full of gaps. Some are narrow, just a few kilometers wide. Others, like the Cassini division, span thousands of kilometers. These gaps aren't empty, they contain particles. But the particle density is much lower than in the surrounding regions. The gaps are maintained by gravitational resonances. A resonance occurs when the orbital period of a ring particle is a simple fraction of the orbital period of a moon. For example, the inner edge of the Cassini division is in a 2-to-1 resonance with Mimas. That means for every one orbit, Mimas completes. The ring particles at that location complete 2 orbits. Every time Mimas passes by, it gives the ring particles a gravitational tug. Over time, these tugs add up. They push the particles out of the resonance zone, creating a gap. The same process happens throughout the ring system. The Encke gap is maintained by the Moon Pan. The Keeler gap is maintained by Daphnis. The outer edge of the A ring is in a 7-6 resonance with Janus and Epimetheus. But not all gaps can be explained by resonances. Some remain mysterious. And that's a clue. It suggests that Saturn's ring system is still evolving, that the gaps are still forming, that the moons and rings are still interacting in ways we don't fully understand. If the rings formed 100 million years ago, they've had time to settle into their current structure, but not enough time to reach a completely stable state. The system is young, and it's still changing. Saturn's rings won't last forever. Cassini measured the rate at which ring material is falling into Saturn, between 432 and 2,870 kilograms per second. That's a huge range because the measurements are difficult and depend on several assumptions. But even at the lower end, the implications are clear. If we assume an average rate of 1,500 kilograms per second, the rings will lose their current mass in about 292 million years. But there's another process at work: ring rain. Charged particles from the rings spiral down along Saturn's magnetic field lines and vaporize in the atmosphere. This process is happening continuously. When you combine ring rain and equatorial infall, the ring's remaining lifetime drops to less than 100 million years. That's short. Remarkably short. In 100 million years, Saturn will look like Jupiter. It will still have rings, but they'll be faint, sparse, barely visible. The majestic ring system that defines Saturn today is temporary. We're lucky to be here to see it. But there's a twist. In December 2024, a team led by Dr. Ryuki Hyodo published a study that challenges the idea that Saturn's rings are young. The argument for young rings is based on how clean they are. Saturn's rings are 99% water ice. They're bright. They're pristine. If the rings were billions of years old, they should be dirty. Micrometeoroids, tiny particles of rock and dust, constantly bombard the rings. Over time, this dark material should accumulate on the icy ring particles, making them darker. But it doesn't. Cassini observed that the rings are remarkably clean, and that observation led scientists to conclude the rings must be young, no more than a few 100 million years old. Hyodo's team questioned that assumption. They ran computer simulations of what happens when a micrometeoroid strikes an icy ring particle at high speed, about 30 kilometers per second. The results were surprising. At those speeds, the impact doesn't just chip off material. It vaporizes the micrometeoroid completely. The temperature at the impact site reaches 10,000 Kelvin. The rocky material turns into a hot plasma. And then something else happens. The plasma expands, it cools, and it condenses into nanometer-sized particles. These tiny particles become electrically charged. Once charged, they interact with Saturn's magnetic field. The magnetic field lines funnel them either into Saturn's atmosphere or out into space. Very little of the material actually stays in the rings. Hyodo's team calculated the accretion efficiency, the fraction of impacting material that remains on the rings. Previous estimates assumed it was 10% or higher, but the new simulations suggest it's less than 1%. If that's true, the rings could remain bright and clean for billions of years. The youth of the rings, as indicated by their appearance, could be an illusion. The rings might actually be ancient. They might have formed 4.5 billion years ago when Saturn itself formed. This pollution resistance mechanism also explains other Cassini observations. The spacecraft detected nanometer-sized particles streaming away from Saturn. It detected water-rich ions raining into the atmosphere. All of this is consistent with the pollution resistance process. But this theory is still new. It's based on simulations, not direct observations, and it contradicts the mass loss measurements that suggest the rings are young. So we're left with two competing ideas. Either the rings are young, 100 million years old and formed from the destruction of Chrysalis or another moon. Or the rings are ancient, 4.5 billion years old, and have been kept clean by pollution resistance. Both theories fit some of the data. Neither fits all of it. And that's where we are right now. Let's step back and review what we know. Saturn's rings are made almost entirely of water ice. They're extremely thin, only about 10 meters thick on average, despite being 270,000 kilometers wide. They contain billions of particles, ranging in size from dust grains to house-sized chunks. The rings are losing mass. Ring rain and equatorial infall are draining material into Saturn's atmosphere at a rate that suggests the rings will disappear in less than 100 million years unless the pollution resistance mechanism is replenishing them. Somehow, the rings are aligned with Saturn's equatorial plane, not its orbital plane. Saturn's equator is tilted 26.7 degrees, and the rings follow that tilt. Saturn's moons have unusual orbital properties. Titan, Hyperion, and Iapetus all have slightly eccentric orbits. Iapetus is inclined 15.5 degrees relative to the other moons. There are gaps in the rings, maintained by gravitational resonances with Saturn's moons. All of this is fact. These are observations, measurements, data. But when we try to explain how the rings formed, we move into the realm of theory. And the theories conflict. The chrysalis hypothesis says the rings formed 100 million years ago from the destruction of a lost moon. It explains Saturn's axial tilt, the ring's alignment, and the moon's orbital properties. But we have no direct evidence that chrysalis existed. The pollution resistance theory says the rings are 4.5 billion years old and have stayed clean through a self-cleaning mechanism. It explains the ring's brightness and composition, but it struggles to explain why the rings are losing mass so quickly. Other theories, comet collisions, TNO disruptions, explain some features but not others. We don't know which theory is correct. We might not know for decades. We might not know until we send another spacecraft to Saturn. But that's okay. That's how science works. We gather data, we build models, we test predictions, and slowly, over time, we narrow down the possibilities. Saturn's rings are more than just a beautiful feature. They're a window into the history of the solar system. If the rings are young, they tell us that catastrophic events, moon destructions, giant impacts can happen relatively recently in a planet's history. They remind us that the solar system is still dynamic, still changing. If the rings are ancient, they tell us that planetary systems can maintain delicate structures for billions of years. They show us that even in the harshness of space, beauty can endure. Either way, Saturn's rings are temporary. In 100 million years, or perhaps 1 billion years, they'll be gone. The particles will have spiraled into Saturn, the rings will fade, and future astronomers, looking at Saturn, will see a world without rings. They'll look at old images like the ones Cassini sent back, and wonder what it was like to live in an era when Saturn had rings. And in that sense, we're fortunate. We're living in a time when Saturn is at its most spectacular, when the rings are still bright, still massive, still visible. We're witnessing a moment in cosmic history that won't last. So, where do we go from here? The next major mission to Saturn isn't scheduled for decades. NASA's Dragonfly mission, launching no earlier than 2028, will visit Titan, Saturn's largest moon. It's a rotorcraft, a helicopter-like vehicle that will fly through Titan's thick atmosphere and explore its surface. Dragonfly will search for signs of life. It will study Titan's organic chemistry. And it might carry a seismometer, which could detect vibrations from Saturn itself and provide new data on the planet's interior. But Dragonfly won't study the rings. That will require a different mission, a dedicated Saturn orbiter. Such a mission could measure the ring's mass more precisely. It could study the pollution resistance mechanism. It could search for evidence of lost moons embedded in the rings. It could, perhaps, finally answer the question, how did Saturn get its rings? Until then, we watch, we model, we simulate, we debate, And we marvel at the fact that we live in a universe where something as improbable as Saturn's rings can exist at all. For now, the origin of Saturn's rings remains one of the great mysteries of planetary science. We know they're there, but we still don't know where they came from. Maybe they're the shattered remains of Chrysalis, a lost moon torn apart by Saturn's gravity just 100 million years ago. The truth is, we don't know. And maybe that's the point. Science isn't about having final answers. It's about asking better questions and learning to live with uncertainty. Saturn's rings have been confusing us for more than 400 years. They were a mystery when Galileo Galilei first saw them in 1610 and couldn't tell what they were. They were a mystery when Giovanni Cassini discovered the great division that still bears his name. And they're still a mystery today. But here's the part that changes how we see Saturn. Because, whatever their origin, the rings are not permanent. They're fading. And for the first time in human history, we're alive at the exact moment when Saturn is beginning to lose the feature that defines it. A planet known for its rings may not always have them. So the question is no longer just how Saturn got its rings. It's what happens when they're gone. That story, the slow erasure of Saturn's identity, is just beginning.